All right, good evening, everyone. Thank you for coming this evening. We've got the wonderful Peter, VK3 BFG, who will be presenting tonight on the Smith's chart. So we're very much looking forward to that. And clearly from the attendance this evening is you're under a lot of pressure. Welcome to those on Zoom. All right, so without any further palaver, I'd like to introduce Peter, VK3 BFG, who will enlighten us on the nuances of the Smith's chart. Thank you, Peter.
Thanks, Martin. That gentleman there worked all of the points out that you see in front of you on that chart in 1939. He didn't have AI. He didn't have pretty much everything that we've got to enable us to calculate these days. He probably would have had a slide rule. That would have been about it to do all the calculations that he did. So it was a magnificent effort. So that's what the Smith chart does, and because of that, it's got a number of applications, as we'll have a look. Those of you that have got a VNA, probably the first thing that you switch on is you get a Smith chart. A fact that you can manipulate that very quickly and work out some networks is all due to this man here. So the chart there contains every possible impedance that could be on any transmission line having any VSWR. But if you look at the chart that you've got there, there's parts of that chart that are not really practical because the lines get very, very close together. So you've got to operate with the Smith chart in that area where it's reasonable graphics. Well, we're talking about impedance, and we'll use the letter Z, and of course it's got the unit of the ohm, but it's a combination of resistance and reactance, as we probably all know, and that's because the voltage and the current's not in phase. Well, it is sometimes, but mainly not. So there's our good old impedance triangle that some of you would have seen when you did your standard course or your advanced course. And for those that have got a foundation licence and looking forward, you will have a look at that. The square root of r squared plus x squared gives you the magnitude or the size of the impedance, and the r tan x on r, which is really just the angle whose tangent is x on r, gives you the phase angle. So that's the inductive case, and that's the capacitive case, just reverse in sense. It could have been the other way around. It's absolutely arbitrary, but somebody decided that we would have inductive reactance vertical like that, and capacitive reactance negative. It could have been the other way around. So we now look at how we actually state an impedance in an engineering sense, and we call it R plus JX. The J actually is the square root of -1, which never works out, but let's not worry about that. What it does do is it provides the 90 degrees that's the required phase for the reactance. So it's just a shorthand way of doing that. So you've got R plus JX, and you've got R minus JX for capacitive impedances. We also deal into the forbidden area for some, and that's the invert of impedance, which is admittance. I think conductance is fairly easy to sort of get a hold of, and that's the real or the the real part of the actual quantity. And then we've got this susceptance. And if you look at the capacitive admittance, it's exactly the opposite to capacitive impedance. Why am I saying this? Well, we're going to be dealing with susceptance and admittance while we're dealing with the Smith chart, because when you're dealing with series networks, R plus JX and R minus JX is the easiest to deal with. But if you're dealing with parallel networks, then the conductance and susceptance concept is easier to work with. And it's just got to do with the sums. You can do either, and I'll show you a couple of examples that are a bit horrifying. So there we are. Z's 1 on Y and Y is 1 on Z. And we've got inductive admittance there as G minus JB. So there's a summary of what we're going to deal with in the Smith chart, both impedance and admittance, both. Sometimes it's convenient to use one and sometimes the other. So we talk about the characteristic impedance of a transmission line, and for people that are studying for foundation, I'm not sure how we can actually explain what the heck that is. But it's certainly got something to do with the physical parameters of the transmission line, as you know. But if you get a multimeter, you can't measure what it might be. So it's a thing that we're going to be working with, and in a coaxial cable, depends on the ratio of the two conductors, of course, and the permittivity of the insulation. Permittivity being one of the properties of a material, really relating to electrostatics. Okay, that's just a little bit of a warm-up. That's the equivalent circuit of a transmission line. At any frequency you like, it will be that. That's particularly appropriate for the old 600 ohm line, where we used to have the telephone system, and that was very definitely the equivalent circuit for that model. But as you go up in frequency, the inductive reactance and the capacitive reactance becomes significantly more than the rest. So it really just comes down to series L and parallel C. And of course, that's a network that you can work with. So here we've got the idea that, yep, a transmission line is something that we use to get our transmitter information up to antenna, but there's the potential to use it for other things because it is a network. And certainly the Smith chart is about that. Well, when we have a mismatch, we get a forward wave and a reflected wave on the transmission line, and they add together to produce standing waves, which are due to the fact that the vector addition of the velocities is equal to 0, and therefore you get the peaks and troughs. And you can observe a standing wave in a ripple tank, which is a device that just generates waves in a tank, and if you have a barrier that you put up and get a reverse wave with it, you'll see the standing wave. No doubt you would have seen standing waves on the beach coming up to waves against a brick wall, and you see the cork just going up and down. Well, it is the standing waves that is the basis of the applications for a Smith chart. And if you know the VSWR that you have on the transmission line, that then dictates all of the impedances that you can find on the Smith chart itself. So there's the Cartesian version of an inductive impedance on the left, and there's the Smith chart version of it, which is just a little dot. So how does that all work? Well, you can see there that I put that, the red part there is where the transmission line is inductive, and the blue part is where the transmission line is capacitive. And again, I've got Cartesian coordinates on the left, where we've got a number of different resistances, and then we transferred that to the Smith chart, and they transfer as circles on the Smith chart. And you can probably see them if you look down on the one that you've got. You can see those circles that are there. So they are the circle of constant resistance. So anywhere around the blue circle, whatever that resistance might be, that resistance is constant around that circle. We then go to inductance, and you can see the Cartesian version there on the left, where we've got the reactance is shown at 90 degrees to the prior graph, which is exactly what we have, and then what the Smith chart looks like. So they're constant arcs. So anywhere along on those arcs, the reactance is constant. We nearly lost things there. So what have we got next? Oh, okay. Just a few more of the constant resistance circles. And of course, there's numbers of them filled in between those digits as well. And we've got more of those as well. And as you fill in the Smith chart with more and more, it gets fairly crowded. And that's why it's, I'm pleased I've got such light here. I can see my examples here very well. But where you're sitting, it would be difficult to see all of the impedances that are there with all of the options that you've got. One end of the Smith chart there, you can see I've notated as being a short circuit. That means it's 0 ohms at that point. And the other end is an open circuit, and that represents infinity ohms. And you can see that the graphs are getting very, very crowded down that end. So if you try to realise a network and you find yourself down in that end, then the network's not realisable. It means that the actual values will change so quickly that it's just not practical. So you've got to try and work with the Smith chart in the areas where you can logically plot a value. But notwithstanding, we do deal with short circuit and open circuit as an example. And by the way, one revolution of that Smith chart represents 1/2 wavelengths. 1/2 revolution is 1/4 wavelengths. So there's the inference that a quarter wave from an open circuit, you might find a short circuit. And I've got an example here where just put that in your transmission line and presuming that the length of that is the appropriate for your application, you've got yourself a notch filter. It happens that the Q of that's not too good, but not sure why that is, but I did do a sweep of it. I think I've got a graph of it here shortly. Anywhere on that Smith chart though...
Peter, would I show it around?
Oh, sure. It's a notch filter. Anywhere on the Smith chart, you actually normalise the values. And that means whatever the characteristic impedance of the transmission line that you're using, you divide the impedance that you're interested in by that value. And that's what we call ZL dash there. You do the same with admittances, except with admittances you multiply because it's the inverse of impedance. So there we are, 1 revolution, 1/2 wavelength. and we've got 1/4 revolution for the half wavelength. And the inference from the Smith chart is that, you know, 1/4 wave away from an open circuit, you've got a short circuit. So the notch filter is an application. That's the plot I did with the spectrum analyzer. I'm driving a signal through from a signal generator into that notch filter, and it's showing that there's notches on a number of places, and of course they're the frequencies, whatever those frequencies might be, are the frequencies for which that's a 1/4 wave, and the open circuit is appearing as a short circuit. And you can see there that you know, you've got about 40 dB of notch there with that. So we got lots and lots of components there, and there's a blow-up of what you're looking at. And there's a scale down below that which we'll have a look at very briefly shortly. Okay, we've got those. You can clearly see there around the short, around the open, just the long way around. Yeah, impedance. Yes, no, that's good. Sorry. Around that open circuit, the impedances are not really practical to work out. So there's an example. I've just taken a couple. We've got a characteristic impedance of 75 ohms in a cable, and then one represents 75 ohms. When you're doing a match on one of these VNAs, the magic thing is to get the thing to be in the centre, and if you're in the centre, you're absolutely matched, which is part of the exercises that we might do. So there's a plot. We're plotting 100 plus J75 using a transmission line of 50 ohms, and you can see the arc that represents the reactance that we're talking about, which is the 75 divided by 50, by the way, and then that circle, which is 100 divided by 50, which is the 2 circle, if you like, and the junction of those two is where the impedance is plotted. So that's okay. Let's say, just for example, that you've got that impedance and you want to transfer it to an admittance. I'll show you the calculation there. We won't stay on it very long because you can see it's fairly convoluted to get the answer. By the way, admittance, the unit is Siemens. So you can see the calculations fairly difficult. There's another option. You can do it via that method and get the same answer, but it's fairly convoluted. On the Smith chart, that's it. You plot the Z, you draw the circle, and then you go directly across to the opposite and read it off, and you've got the impedance. So it's pretty easy. So there's an impedance that we plotted, and there's the admittance. Now you've got to remember when you realise that admittance, you've got to multiply. You've got to divide by whatever the characteristic impedance of the transmission line is. Whereas with the Z, you've got to multiply by. So you end up with fairly small numbers for the admittances. There's an example where we've got 0088 minus J.0148. And anywhere where you plot an impedance, like we just plotted 30 plus J50, if that happens to be the load that you have, and you draw a circle, well, all those points on the circle are all the impedances that you generate with that load and that characteristic impedance. And you can you can do work with that. Again, just back with the theory that you might have got somewhere along the line, there's an equation that says if you want to transfer a certain impedance to another impedance, meaning that ZS is the sending end impedance that you have, and ZR is the load impedance that you have, the product of those, and take the square root of it, is the transmission line that you would need. So I did a calculation of that, just as an example. I think we've got it here. Yeah, that's it. This was a 23 centimetre problem for me. It looked as though I was going to have to bring in 4 different antennas to the one feed point, and therefore how am I going to match that? So a quarter wave transformer is what we used, and there's the antenna end, which is 50 ohms, and then we've got 4 in parallel, meaning that we've got effectively 12.5 ohms to transfer to 50 ohms. So let's see how we do that. There's a little calculation where we did the square root of Z sending and Z receiving, and the answer to that was that you need a characteristic impedance of 25 ohms to do that. And that's the actual realisation of what happened. That's a quarter wave at 23 centimetres. It just so happened that that standard aluminium stock, together with a circular piece of brass from the hobby shop, worked out pretty close to being right. And you can test this by putting 450 ohm dummy loads on it, and then you look in there and you've got your 50 ohms. So that's just an example of what we did there. And we're talking about a quarter wave at 23 centimetres. Oh, there's a picture of it. You can see the brass that got from the hobby shop and the rectangular aluminium, just per chance. No, well, I guess we did the maths, and we looked up the ARRL resource for that to find out if we could get some kinds of shapes. And of course, you can have conductors within conductors of various shapes, and that generates various impedance transmission lines. So I was just very lucky that a lump of copper from the hobby shop was exactly the right diameter, and that extrusion of aluminium worked out fine. And yeah, the match there is very, very good. It's very close to being exactly right. We've got some scales down below, and they're going to show some surprising things. Okay, this is the problem. We've got a transmission line, and it's got 3 dB of attenuation, and your VSWR meter is reading 1.45 to 1. So we go to the Smith chart, and we plot that up. And I've shown actually 2 different examples. On the left there, you can just read the VSWRs that are appropriate. But on the right, there's an attenuation scale in decibels. So we've got 3 dB of attenuation, and we're currently on that inner circle. That's the VSWR that we're seeing on our VSWR meter. But then we walk up the transmission line and lose 3 dB, and then you can see the big 3 there, or you go back up and you've got a significantly bigger VSWR. And then if it was 4 dB, it's even bigger. particularly at VHF and UHF, you can't measure the VSWR of your antenna down at the antenna. At HF, well, you've probably got lower losses, but if you've got a long line, 3 dB is not a hell of a lot of loss really, but there it is. Big difference. So read the attenuation there. So that's a surprising result really, when you sort of look at that. A bit sobering in one way, but yeah. So when I hear people saying, oh, I got a good VSWR and we're on 2 metres or on 70 Siemens or 23 Siemens, even worse, yeah. On 23 Siemens, depending on how long the transmission line, it could be open circuit and you wouldn't know because the attenuation's so high. So there we are, with 3 dB loss, the VSWR came back to 2.4 to 1, or up to, which is a significant increase. And then 1 dB more, it's even worse. That's 3.2 to 1. So you can see that it's getting worse very quickly as you add some attenuation on. Remember, this guy did all of his calculations with a slide rule. No calculator, no AI, nothing. So yeah, this is an example of a couple of impedances or reactances. Seem to be blinking. And you'll see on the Smith chart, there's a direction that's towards the generator. That means that, in effect, you're standing at the load and you're looking towards the transmitter. Or the other option is you're looking towards the load, so you're actually at the transmitter end looking at the load. So both of those things are there, and they're very small arrows. I've got the red and the blue up there. But if you look very closely at the chart that you've got, those directions are there. There's just an example of selecting an impedance from the Smith chart, then taking it back to being the exact impedance, which is the J50, and then using the reactance formula, you come back to 18.4 nanohenries. Now what does that mean? Well, it means if you go from an open circuit around that away, that far on a transmission line, you're going to end up with an inductance of 18.4 nanohenries. And if you go the other way, there's the actual length. If you go the other way, you'll get a capacitor. So, damn it, you can actually make inductors and capacitors out of these things. And those of you that had a look in solid state amplifiers, you'll often see just a line that's sort of hanging off the main transmission line, and that could be a trap, but it also could be a capacitance or inductance. You can actually trim the length of those and vary the amount of capacitance. And you can see you were talking about pretty small capacitances there, but you can accurately put a transmission line on a piece of printed circuit board to a fair degree of accuracy. So yeah, we use transmission lines as capacitors and inductors. So that gives you an idea of how the impedance sort of transforms as you go around the Smith chart. You see there it starts at 0 and then it goes to an infinity and then ends back at 0 again at the half wavelength. The middle part there is the quarter wavelength, and we're starting at a short circuit. So quarter wave from the short circuit, we've got an open circuit, and then another quarter wave, we've got the same impedance again. And those shaded areas are the reactances that you can generate. And of course, some of those are practical and some of them are not. Of course, I'm choosing the ones that are practical. Now, there are some Smith charts, and you haven't got one because they're colour and they cost me 50 cents a shot, that have got both impedance and admittance on them at the same time. And that means you can sort of go from one to the other, and it makes life fairly easy if you've got one. Well, I'm not sure why I put that in there, but that's the game with the VNA. If you've got one of those VNAs to get the impedance at the centre, and it might wander around exactly like that. Not sure why I put that one in there, but anyway. Let's go to this. Oh, okay. Here's another example where we've got an impedance that we measure with our impedance meters. We've all got 25 minus J, 50 is there, and we want to get an impedance of 50 ohms to match to our transmission line. So we can use a piece of transmission line, and also we can use either a short circuit or an open circuit stub, the stub being that red thing that's just in parallel with the blue main line. So let's have a look at that. There's my impedance normalised, and I just take the circle around to that axis there, and you can actually read off the VSWR there. That's generated by that impedance on the Smith chart. And there's the plot of that's actually the stub that we need. If I go back one, I'll leave it there. That the prior graph where we rotated around dictated how far you move down from the transmission line, and it's in wavelengths, and then you end up with either an inductive reactance or a capacitive reactance to tune out, and you tune it with an open circuit or a short circuit stub. And this little calculation that I've done here is for that. So there's the values. And on the scale there, we're 0.365 lambda, and then we end up at 0.428 lambda. So you've got to subtract those to get the actual length required. And we started at the impedance that we have, and we rotated until we met the admittance equals one line or circle. Now, you won't be able to see it because you haven't got that chart, but it is there, and you're looking for that, because at that point there, you've actually got a match. All you've got to do then is tune out the capacitance or the inductance that you might have. So there it is. That's how much we've got to tune out. 1.6. Let's see what that calculates to. Let's come back up here. Up here. There's the length of the open circuit stub. Or you can use a short circuit stub and get the same result. And there's the answer to the question and the calculations that go with it. Now, I realise that was pretty quick, but it's just an example of how you might use the Smith chart to do some matching. And there's the calculation of the actual length that's required from the wavelength and the frequency. I think that was 432, that one. Not sure about that. I'd have to think about it, yep. Because the reactances are fairly small, and you can often just generate the things with a PCB. Finally, we'll have a quick look at L matching networks. And I mentioned earlier on that you might find that you select the network and it just can't work out on the Smith chart. That means you've selected the wrong network. That's all there is to that. So you put that one aside and try another one. You can see there all the different possibilities of either series C and shunt L, or series L and shunt C, or parallel C or parallel L, etc. All the different options of producing a match to the little rectangular thing which is your load. So I've selected one here. It's a better graph showing you what networks work in what areas of the Smith chart. And as I mentioned, if you try a network and it just doesn't seem to work out, you've got the wrong network. So this one is very, very simple, and I've used the dual chart. So I've got a load and measured at 75 minus J60, and we want to match that to 50 ohms. So I start, you can see there, I start at 75 minus J60, and I move around that circle, and I move a total reactance of 0.32 plus 0.5. And then I move in the opposite direction, down towards the centre, and that's the prize. So it's very, very simple using the admittance chart and to solve that network. And again, if you started at a point and you plotted it up, and you did your circles around and you didn't end up at the middle, well, you got the wrong network. But this one did. So there we are, there's the calculations. And we end up with 22.5 nanohenries as the required one there. The frequency is 432, so I think I did the calculations for that. Yeah, we've got 6.14 puff and 22 nanohenries for that network, where we've got series C and shunt L. Now, if you look at the chart again, where I was dealing with the inductor, I was actually in parallel, and therefore I was using the susceptance part of it. And then, when we're dealing with the capacitor, that's series. So then I jump back to the impedance part of the network and just run down there. So that dual Smith chart with both admittances and impedances makes networks very, very easy to manage. So there are a couple of examples of what you can do with the Smith chart, and it's all history in the sense that we've got all sorts of really good gadgets that help us out to do all of those sorts of things. But at least now, when you switch on your VNR and you see the Smith chart, you realise that there's a whole lot of stuff that's behind that. And the gentleman that did the original calculations was an incredible scientist, that's for sure. So short and sweet. Thank you.
Are there any questions? All right, on behalf of everyone this evening, I'd like to thank Peter for a very detailed explanation of the intricacies of the Smith chart, and I hope it's given some of you a better understanding of its use, particularly in the more technical aspects. One word of advice for the foundation members, don't panic over it. It's far, far, far above what you need to worry about. So again, I'd like to thank Peter for giving up his evening and preparing the presentation. Thank you very much. Well done.